Hello, hi everyone. We're going to go ahead and finish up Unit 3 today. So we're going to do this one page of applied optimization problems, and then we're going to do the last 1, 2, 3 pages of antiderivatives. So let's start off here. Now, optimization problems are going to involve our 3.2 material, where we're learning maximum and minimum ideas. But in here, we're going to abuse the fact that at critical points is when we have relative maxes and relative mins and things of that. So let's go ahead and start off with example 1. A rectangular has a perimeter of 40 meters. Find the dimensions that maximize its area. Okay, so that's a bit weird, but let's turn its area into a math problem. So we know that the area of a rectangle is length times width. Now, we also have the added detail that the perimeter must be 40 meters. So we have another detail that if I add 2 lengths plus the 2 width, I should get 40. Now, we can rewrite this as a function of one of the variables. I'm going to pick W. So let's start off with turning L into W using this formula. Well, using this formula, we know that we can divide 2 from everything. So L plus W equals 20. And then I know L can be written as 20 minus W. So I'm going to go ahead and add that into here. I get A is equal to 20 minus W times W, which later becomes negative W squared plus 20W. So this has now become a function of W. Well, we know that this is a parabola, and we can treat this like this shape. And what's at the top of the shape? This maximum point. Now we know from our max and min ideas from 3.2 that we could technically find not this value, but the value of its derivatives critical points. So I'm going to do a derivative. We'll get negative 2W plus 20. And we're going to go ahead and solve for when this guy is equal to 0. So, or here, let me go ahead and bring it over here. We'll do that A is equal to 0, so that means negative 2W plus 20 is equal to 0. From here, before I do anything, I see that these are even numbers, so I'm going to do my best to just factor out. So W plus 10 is equal to 0. And then I'm going to go ahead and add W to both sides to get 10 is equal to W. So that's our answer. The W is 10. And then we use the formula for L. So we know that L is equal to 20 minus W. And we said that the max, or we're claiming that the max W is 10. So that must mean L must be 20 minus 10, which is just 10 itself. So it seems like W is 10 and L is 10. And it seems like that will maximize this area. Now, the idea of this as well comes from, well, how do we know that that's max? How do we know it's not, let's say 11 and 9? Well, again, you chose to turn this area formula into a formula that has only one variable right here. And we know this one variable, either you can graph it or you can infer it. It will have one critical point. Or not one critical point, it will have a critical point, right? Now, from that, you could technically argue, well, we don't know if it's a max or min, right? I did abuse the fact that we know that it's of this shape. So we know that its derivative's critical point will only have that peak. Well, if that were the case, you can also do the first derivative test as well. And if we have, 10 being our critical point, then we can go ahead and evaluate something to the left of 10 and right of 10. So I'm just going to use 9 and 11. And we'll use, we'll just plug it in. Negative 2w plus 20. I had the habit to, give all the factors, but in this case, we just have the one idea. So from here, I know if I plug in 9, I'll get negative 18 plus a 20, so that'll be positive. And if I plug in 11, I'll get negative 22 plus a 20, so that'll be a negative value that comes out. Um, specifically positive 2 and negative 2. But we see here that we'll have, from that 10 on our number line, we'll have a rise because the slope is positive, and then a down because the slope to the right of it is negative, which means, visually you can see that there will be a little hill forming. So keep that in mind. Now, granted, you would double check things like this if you were maybe given a trick question. I don't believe in trick questions without proper warning. So, for example, there's a question that's like this that's gonna be like these, or more. It's probably gonna be more like these, um, on the final. Well, I mean on the final on the your test 3. But technically speaking, I'd really like to warn you of trick questions, so I will say something like this is a trick question. Maybe I'll provide a hint, but I don't think you'll see that in this course, truthfully. Maybe on a final question, question on the final, but I don't think you'll see that here from me. Okay, let's move on to this one. So this is you want a rectangular enclosure next to a river, where one side is a river and there's no fence. Um, so let's go ahead and I guess if we draw a river, right, then we have this fence right here, because it says rectangular where one side's river, no fence. Okay. And it says fencing costs 10 per meter for the two sides perpendicular to the river. So that means this is 10 per meter. Both of these are 10 per meter. And this is 20 per meter. The 20 side parallel. Okay. You have a budget of $600. What dimensions maximize the area? So you're almost dealing with this problem again, but with a different coat of paint. It's a little bit tricky though, because technically, you know that the area is length times width. But we don't have the one-for-one same luxuries that we do about the parameter. Perimeter. But what you do have is that for $600, you can get 10 times whatever our, let's call this length. Whatever our length will be, plus another 10 times whatever the length will be, plus 20 times whatever the width will be. If you're doing this, you could also switch the L and W's, but just keep in mind, here, I'm going to write it here just on the side that we're doing. The up and downs will be L. Let me do better, L. And then the horizontal left and right will be W. Okay. So, not exactly the formula for perimeter, but we can still construct a formula given that budget idea. Well, we definitely can simplify here. And you'll get, actually here, let's start off with simplifying already, taking out every 10. So 10 here, 10 here, 10 here, 10 here. That's to keep in mind though, that, you factor out a 10 from each of these guys. And remember, you can't just factor out one term. If it's a combination of terms, you have to factor out each term. The technical step, if you want to be technical about it, is doing this. But I just chose to skip that with the classic crossing out a W notation. So we have 60 is equal to, well, I can say 2 L's plus 2 W's. You can also factor out a 2 now in this case. So that becomes 30 plus is equal to L plus W. And then you have a similar trick where you can definitely go ahead and make a substitution for L or W. We did W before. It's not going to change if you did L, but let's go and do W. I mean, use let's find something for W to make this function be of L's only. So W is equal to 30 minus L. I'm going to plug it in here. A is equal to L times 30 minus L. And then I'm going to go ahead and distribute this to be L squared, or negative L squared, sorry, plus 30L. And then I'm going to do a derivative. This time with respect to L, you'll have negative 2L plus 30. And we're using the idea again of the critical points. And we're also, we saw it here a little bit and we see it here. We're going to take advantage of the fact that this is negative. So we know that this parabola will be in this shape. So we just need to find the critical point, and that should be our max point. Let's go ahead and solve for when this is 0, because we're doing a critical point. And to factor out the evens, we have 0 is equal to negative L plus 15. And then I'm going to go ahead and add L to both sides to get a pretty L is equal to 15. So if L is equal to 15, that means that, because we use this formula, that W will also equal 15. And those are the dimensions that maximize the area. Okay? So please keep that in mind. The trick here, it was very tricky, was that we have to manipulate the given formula so it's of one variable. And then we use our classic min and max ideas. Let's do this last one. A company's price P in dollars and quantity X sold satisfied, P is equal to 20 minus 3X. Find the X that maximizes the revenue. So revenue. All right, let me do a capital R because that might look like radius. Revenue is equal to the price per item times how many items we sold, and find that price. So given the revenue formula that I've written here, we have P times X. And sure, you could technically make it a function of P or a function of X, but it's a bit easier to make it a function of X since we already have something that says P equals. You could go the roundabout way and, get the X equals from here and plug it in, but I'm just going to go ahead and do the easier thing. 200 minus 3x all times x. I'm going to go ahead and distribute this to make it a little bit prettier. Negative 3x squared plus 200x. Here, we're also going to take advantage of the fact that that is clearly an upside down parabola. And we're going to perform the derivative of this with respect to x. So negative 6x plus 200. And we're going to do the idea of the critical value. So 0 is equal to negative 6x plus 200. I'm going to go ahead and added the 6x. Or I could have done the even trick here as well, but I'm going to go ahead and do it later. We're going to go ahead and solve for x. So x is 200 over 6, which we can simplify to 100 over 3. So this is going to be the quantity sold that will maximize our revenue. Obviously, this is, a fraction of a quantity, but the idea here is that we want to get as close as possible. So I'll leave it like this, but then the final answer, I'll do some rounding. But we need to make sure that we also need to find the price as well, because we want to find the quantity that maximizes the revenue and the price. So the price formula was up here. So this is price is 200 minus 3 times 100 over 3. Well, that will cancel out. And that will be 200 minus 100, and that's just going to be 100. So the price is 100, and the quantity sold is 100 over 3. Now, technically speaking, that's not as proper, but if you wanted to, you could round. You could say x is approximately, we'll do, that's going to be 33.333 forever. So let's just round to 33. And then if that's true, then if we plug that into P, 200 minus 3 times 33, which is going to be 99, then you're going to have 101. So this is also kind of a solution as well. This one's just more exact, but this is probably our preferred solution because in this specific realm, we have to sell items, and you can't sell 33 and a third of an item. That doesn't make sense. But if we wanted the pure like mathematical analytic answer, then it would be this and this. So yeah. Um keep in mind the homework as well. This homework that you're getting for this will be short, and you're also not getting a worksheet for this section, which is good, but keep in mind that it's only because it's a dense idea. All right, let's go to antiderivatives. So antiderivatives. So we need to review a couple of things, and this is kind of also a pretty nice like bow on top of everything we've learned so far. So first, rules of exponents. Just that quick review. Remember, if it's on the bottom, x to the power of a, that can be written as x to the power of negative a, and put it on the top. Square root, don't forget that it's a fraction. And in fact, if you were doing an nth root, it's just x to the power 1 over n. All right, let's review derivatives. So keep in mind that for some of these, I haven't been as strict with the constant idea since we have this, but these include the constants. So don't get it too twisted. It's not anything too different, but it's just something extra to like make it easier, but it shouldn't confuse. Okay. First, we know that if it's a constant times a function, we can take out the constant and still do derivative of that function. If we're adding or subtracting, we can distribute the differentiation. If we're differentiating with respect to a constant, that's just going to be 0. If we're differentiating with respect to a constant times x to some power, then we can use the power rule, which will bring down that power, and then we take away 1 from that power on top of x. If there are two functions multiplying, then that's called the product rule. If there are two functions dividing, that's called the quotient rule. If there's a function within a function, that's called the chain rule. Everything else here, keep in mind, this isn't new, but just reiterating, if it's a chain rule idea combined with the power idea, then you're basically doing the chain rule combined with the power rule. Okay? Similar ideas for sine, cosine, tangent, secant, etc. Let me see here. Then we have for inverse functions as well. And then we have for exponential, not an exponential, but something taken to the power of something else, and then ln. Okay, so this is not, again, this is not to serve as like, glorified like review, but it is like a where are we now? Combining a lot of ideas stacked on top of each other. And with the idea of stacking things on top of each other, we're gonna practice some derivatives. So if you want, you can even pause the video, I would argue, and you can perform this derivatives with me as we go along. But let's go ahead and do this one by one. So actually, I'm gonna try my best to color code here, just so that way we can go ahead and follow along as closely as possible. Okay, so we have f prime, this gets turned into -2 times 7 x to the power of 6. You bring down the 7, you subtract 1 from it. This becomes a negative sine of x squared times the derivative inside that, which is just 2x. And then this becomes 0, plus 0. From here, we can definitely simplify. That's going to be -14 x to the power of 6. And that becomes a plus sine of x squared times, or yeah, I'll put the 2 here and I'll put the x here. Alright, I think it's more proper to put the x here and then put the sine. It's not too big of a difference. I mean, we know with associative commutative properties that 3 times 2 is the same thing as 2 times 3. But I think it is more common that you put constants first, the variables in alphabetical order, and then functions of a variable after that. Okay. So it'll be our f prime of x. Okay, let's keep it going. This one is definitely going to be ugly. We got a -2 times 1/2 times all of this. Here, I'm just going to go ahead and already do this. Square root of 3x squared minus 2. And times derivative of that, which is just 6x. And then times the derivative of this, which is just a negative sine of 3x times derivative inside that, which is just a 3. So here, that's going to simplify, and we're just left with 6x. So I'll do negative fraction 6x over that square root 3x squared minus 2. And then plus 3 sine of 3x. All right, let's keep it moving, keep it moving. Oh, I'm doing these out of order because it's 1, 3, 5. Let's just go like this. It's not too crazy. Over here, -3 times the derivative of tangent, which even I forgot. I think I put it here. Yeah, secant squared. Secant squared of x squared times derivative inside, which is 2x. And then derivative of this is just -2 times e to the 4x times derivative of the inside, which is just 4. So this gets simplified to -6x secant squared of x squared, and then minus 8e to the 4x. Okay. Right, then over here, well, there's not really any point in doing this piece by piece. We got 4 times the derivative of sine inverse, which is just 1 over the square root of 1 minus parentheses 2x squared squared, and then times the derivative of the inside of that, which is just 4x. Okay, well, there's a couple things we can simplify. Let's combine the, oh, that's not correct. Let's combine these. 4 times 4 is 16. We'll do the x, and then we'll simplify that power inside the square root. So 1 minus 4, x to the 4. F prime of x. Okay. All right. Let's keep it going. We're halfway done with this page. And that's because this is all review. Keep that in mind. Next we're gonna go ahead and do this. Again, I'm gonna do one quick rewrite though. I'm gonna say -5 e to the -3. Okay. In that case, that becomes -5 times -3. Oh, I'm kidding. Give me a second.